Hello, Jeff Disher here again. Today I'm going to talk about function calls and recursion as the lead into a request I had for discussing the merge sort algorithm. So first of all, this topic is kind of targeting people who have a fairly good technical background, can basically understand how things like C programs work, or equivalent Java, C++, something like that. So I'm going to go through the basis for it fairly quickly, but it does require understanding what a function is and how that works. So basically, a function is just a piece of code which takes arguments or parameters and can return a result. And it has local variables that it can use for its own temporary storage. A good example being this function to multiply two numbers together. It takes parameters x and y, returns the result by multiplying them together. So stack frames are another thing that needs to be understood. First of all, programs always execute on something called a stack. This is just a piece of memory that the program can use as temporary storage for performing intermediate operations. Now, what this means is there's always that memory available, and this is where your little temporary local variables and everything are stored. In fact, how it's actually organized is each function stores all of its arguments and locals into its own chunk of the stack called a stack frame. So frames are pushed onto the stack when you're calling a function, and they're popped off when you're returning. If you have a background in computer science or with programming, there's often people talk about things called stacks, which are not necessarily the stack. They're just other data structures which behave the same way, and they have this pushing and popping behavior to them. Basically, you can think of it like a stack of dishes. You can only ever operate on the very top, otherwise you're going to break the stack, so it doesn't work. So you're pushing things onto the stack when you're making it larger, and you're popping things off when you're making it smaller when you're done with them. And that's exactly the metaphor to use here. So all functions are always being run in this. And the other thing that's convenient about this and important to realize is every time you invoke a function, it gets its own storage, its own stack frame. So a simple example of this would be the multiply function from earlier. Say I want to calculate the result of multiplying 2 and 4 together. Well, what that would look like is we'd have a stack frame for func, which has the storage space for 2, 4, and result in it, the local variables that we're using in the function. When we go to call multiply, we'll push another stack frame onto the stack. This is going to be multiply's stack frame. It's got temporary storage for x and y, its parameters. Now these are copies of 2 and 4 in the caller, but that's not a detail of that's not something that is relevant to the actual function itself. Multiply doesn't know how it's been called, so it just takes a copy of whatever it was given and it operates on those. When it's done, it's popped off the stack and the result is returned. So a recursive call is when you take this to more of a kind of an extreme. The idea is that, first of all, a function has no meaning until it's called. And what that means is it's just a piece of code somewhere. It doesn't have any storage, doesn't have any data associated with it. It's just code. When you call it, that's when a function actually is put onto the stack, it's given a stack frame, and given storage space to run in. But this also means that there's nothing special about a function executing. A function could call another copy of itself. All it does is push another frame onto the stack. The code itself doesn't know how many copies of it are currently running. And this is very powerful. So what makes this effective is that each copy of the call, each invocation of the function, has its own copy of the variables and arguments and local variables. So why would you use recursion? Why would you have a function call itself? How does that work and why would you do it? Well, first of all, a lot of problems are defined in terms of themselves. What that means is you can often look at a large problem and realize smaller parts of this problem look like the larger problem, just smaller versions of it. Certain kinds of sorting, like merge sort, certain search algorithms, and just certain other computations that are performed. It's often a very easy way to look at it. This is often referred to as a divide and conquer approach. It's you take a very large data set and then you call the function on the smaller parts of it, thus dividing it in order to make it easier to solve. That's exactly how merge sort works, which I'll get to in a future talk. For people with a math background, consider a proof by induction. It's exactly the same idea. Proof by induction is the same thing as recursion. In fact, some people call it proof by recursion, except it's algebraic, whereas this is physical. So a good example of something which you can generate using a recursive function is the sequence of Fibonacci numbers. 1, 1, 2, 3, 5, 8, 13. These are all, and this goes on and on and on forever. but you can always generate a Fibonacci number by adding together the two numbers that came before it. So, a function, to express a function algebraically that does this, Fibonacci number n is number n minus 1 plus n minus 2. And the special cases we need to keep in mind, so this doesn't go on forever while you're calculating all the numbers, is the 0 number is 1 and the 1 number is 1. And this way, that's how you terminate the decision to keep recursing further and further down. You have what's called a base case. So, a recursive example. Here's an example of the Fibonacci sequence, the algorithm I described before, of how to calculate it. And we're just going to calculate Fib2. A very simple example. So in this case, we first call it with 2. So the nth number we're calculating is 2. First and second are unknown, and we'll default the result to 1. Now, since n is greater than or equal to 2, well, nth in this case greater than or equal to 2, we're actually going to call another copy of ourselves to calculate first and second. So we call it for first. In this case, we pass in nth minus 1, here being 1. We realize that that is not greater than or equal to 2, so we return the result of 1. This means that when we pop that off the stack, first is now updated to say 1. Now we call second, this time with 0 as nth. Again, we don't have to go inside the if, so we return 1 when popping off the stack. Thus, second becomes 1. We now can calculate result as being 1 plus 2 is 2, and we return the result as the Fibonacci number at 2 is 2, which is correct. From before I said 1, 1, 2, 0, 1, 2 numbers, that's how you get it. So, other notes just to explain some more of the background and how this works. Every function requires what I referred to before and what everyone usually refers to it as when you talk to them, is what's called a base case. There's the idea of a recursive case, the part of it that calls itself again, and the base case, the part of it that you already know the answer to. We'd said the Fibonacci numbers at 0 and 1 were 1, so stop recursing, that's the base case. When you reach those values, you just return right away and you know the answer. The other thing to keep in mind is the stack, while it's very cheap, you can always get memory there very, very quickly and cheaply, it's always fast, it's not infinite. There is a certain amount of space there. You're using up memory. So you can't just say, well, I'll call this function and it'll go a million stack frames deep to calculate something complicated. You might start running into problems. Also, because of that, you want to try using loops instead if you ever can. This is because loops execute in a finite space no matter how large their input, whereas recursive functions, they use more stack frames the larger the input is. So the thing that's kind of an interesting takeaway from this that goes beyond some of the immediate things I'm going to use this for in future talks is a concept called dynamic programming. This is kind of like when you take the idea of how recursion works, but instead you change the order in which you execute it such that you never duplicate data. You basically pre-calculate the values that you need by understanding how they're connected to each other as a recursive kind of structure. The reason why you would do this is to avoid duplicate calculations. For example, the algorithm for Fibonacci I showed would not actually scale very well in practice because, for example, you want to calculate Fibonacci number 4, you're going to calculate the intermediate value for Fibonacci 2 twice, just because of the way we'll call through it, and that's how it works, which is fine until you realize that can be very, very time consuming. As the numbers get bigger, you're going to be throwing out most of the data and recalculating it all over again. Wouldn't it be great if you could just store it off to the side? So dynamic programming is a very popular concept in actual deployment once you start trying to build software that actually has to run in reasonable time with simple devices, things like that. But I'm not going to get into it in any nearby talk. Eventually, maybe, because it is an interesting concept and it is overlooked, and a lot of people forget about it, especially in interview situations. So that's the basics on recursive programming and recursive function calls. So I'm going to be able to use that to get into a talk about merge sort and some other sorting algorithms and search algorithms. But to begin with, if there's any questions about this, leave a comment in the thread or send me an email and I'll see what I can do. Anyway, have a good night. Thanks.